Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Cecilia Lunardini, who is Professor of Physics at Arizona State University. One of her primary research focus is neutrinos. Welcome, Cecilia.
Thank you.
Yeah, thanks for doing this. So I know that you have done a lot of work on neutrinos. You have a few papers that came out recently, and I want to start with your 2018 paper, Dirac and Majorana neutrino signatures of primordial black holes, in which you say we study primordial black holes, PBHs, as sources of massive neutrinos via Hawking radiation. Under the hypothesis that black holes emit neutrino mass eigenstates, we describe quantitatively how the PBH evolution and lifetime is affected by the mass and fermionic Dirac and Majorana nature of neutrinos. Before we get into the details, Cecilia, I want to get some definitions. I know that folks would know what black holes are. We had a few episodes on black holes. Here we are talking about the primordial black holes. These are black holes that are formed very, very close to the Big Bang. And there is this phenomenon called Hawking radiation, the black holes evaporating, so to speak, and that radiation is emitting these particles called neutrinos, right? Do I understand that correctly?
Yes.
So primordial black holes. Before we get to the neutrinos, what is sort of the mechanism of formation there? How exactly would they have formed?
Sure. We believe that primordial black holes could form in the early universe from density fluctuations. So we know that any object can possibly become a black hole if you compress it into a very, very small volume.
Yeah.
So the same process could happen in the early universe with density fluctuations. There could be a regional space where there is an overdensity compared to the surrounding.
Yeah.
And if this overdensity is compressed, then it could get to the point of becoming a black hole. The details of this process are beyond my expertise, but this is a fairly reasonable thing to expect.
Yeah, and these are really small, right, in the grand scheme of things?
Yes. So when I started to learn about primordial black holes, I was amazed by how different in mass can they be. They can be maybe the mass of the moon, but they can also be the mass of a bean,
Yeah.
or they can be even smaller. So they can really be very, very tiny.
Yeah, so that's really, really small. So this is sort of quantum fluctuations in early universe, kind of getting concentrated in very, very small areas. But why do we believe those primordial black holes emit neutrinos?
We have to go back to Stephen Hawking for that.
Yeah.
Stephen Hawking wrote this seminal paper, which is about what we nowadays call Hawking radiation. So he demonstrated that any black hole, regardless of what it is, it could be a primordial black hole or a stellar black hole, it doesn't matter. Any black hole isn't really black because it emits radiations, so radiation particles, and that's the process that we call evaporation. So because black holes are fundamentally gravity objects, they would emit any particle that couples to gravity, including neutrinos. So it's the moment you have a black hole, you do have Hawking radiation, and neutrinos are just a expected part of Hawking radiation.
Yeah, so Hawking radiation, so that happens to every black hole, even the supermassive ones, right? So it's a general phenomenon. And so going to neutrinos now, we don't we don't typically think about neutrinos, right? Hadrons and electrons are very well known, but neutrinos are particles that don't interact with matter as we know it, right? So don't interact much with matter. So we don't really see them, we don't really feel them, and so it's difficult to measure them.
That's right.
And so just could you give what is the history of neutrino? When did we first understand such things existed?
Let's see. We go back to the 20th century. And the story goes that the father of neutrinos is Wolfgang Pauli. He made the hypothesis of a new particle existing as a way to explain some strange behavior of neutrinos that were produced by nuclear decay. So it's a long story, but let me just say that for a long time neutrinos were just a hypothesis, and then around the mid of this 20th century, they were actually observed. So we started to know that these particles existed, and but that was pretty much it. So we didn't know much about their properties, and one of these properties is the mass, which we still don't know, amazingly, after all these decades. But we still don't know if the neutrinos have something like a magnetic moment, for example, and something that we didn't learn until much later on is the fact that neutrinos oscillate. That's something that was somehow established at the turn of the century, around the year 2000, really, after decades of testing with solar neutrinos, atmospheric neutrinos. So there are still a number of unknowns on neutrinos, and one of them is the mass. The other one is the nature of the neutrinos being Dirac particles or Majorana particles, which is kind of a fundamental concept. So that's related to the fundamental nature of the neutrino as a particle.
Right. So we know they have a mass, but the mass is very small. Do they have a charge?
Neutrinos don't have a charge.
Yeah.
So they are electrically neutral.
Yeah.
And that's probably the biggest reason for them to be so elusive, as you were mentioning earlier on. Especially early in the 1900s, all the particle detectors were basically electromagnetic detectors. They were looking for charge or magnetic behavior of some sort. So neutrinos don't have that, and so they only have the weak interaction that we know of, and gravity, of course, and so that's why they escape detection so easily, because their interaction is very weak.
Yeah, so that's sort of the beauty of neutrinos, right? So because they don't interact, we can go back billions of light years and perhaps pick up one on Earth, and it would have traveled that distance through all sorts of things, but would not have been affected by them, right?
That's right.
Yeah.
Yes.
And so the other phenomenon of neutrinos is that, yeah, you mentioned that they oscillate. So there are flavors of neutrinos. They go back and forth.
Yes, it's actually a fairly easy to describe quantum phenomenon.
Yeah.
We know that in quantum mechanics there is this a particle is described by this function which is called the wave function, and so the neutrinos could be a neutrino could be born as say an electron neutrino, and then its quantum wave function would evolve over time in a way that after some time the wave function is no longer a purely electron neutrino wave function, but it has a little bit, or even a lot actually, of a different flavor. It could be muon or tau. So what we observe in detectors is this change of flavor. And perhaps the most striking demonstration of this phenomenon is solar neutrinos, because we know that the sun produces electron neutrinos, and it doesn't produce muon and tau neutrinos. So, but here on Earth, we do have evidence that the solar neutrino flux that we receive has some muon and tau neutrinos in it, and that can only be explained by oscillations. And actually, after the solar neutrino data showed this phenomenon, this was also confirmed by, say, man-made experiments. So it's a fairly established phenomenon.
And so the three flavors are electron, muon, and tau.
Yes, that's right.
And so, did I understand that? So, when they are made in the sun, for example, they are made as electron neutrinos, and by the time they reach the Earth, they oscillate into muons and tau.
Yes, yes, in part,
Yeah.
that's what happens. Yeah.
Uh, so, is it always the case that they get manufactured, so to speak, as electron neutrinos always?
It depends on where they are born. There are places where neutrinos are born in all flavors. So it really varies with the type of environment we are talking about.
Okay, okay. And so in the paper, you say PBHs, this is primordial black holes, we talked about, radiate right-handed and left-handed neutrinos in equal amounts. So what do you mean by right-handed and left-handed neutrinos?
Okay, let me see. So,
Uh,
yes.
you say in the case of Dirac neutrinos, PBHs radiate right-hand and left-hand neutrinos in equal amounts, thus possibly increasing the effective number of neutrino species, NEF.
Yes.
Is that explainable? Might be too complicated.
Yes. So, right-handed and left-handed neutrinos, that may take a while to explain what that exactly means.
Okay.
But let me just say that it's related to the neutrino mass. So if neutrinos didn't have a mass, which we know they do,
Yeah.
but if they didn't have a mass, they would only exist as left-handed particles, which means that basically their spin is anti-aligned with their momentum.
Okay.
And but if they have mass, and if they are Dirac particles, there could be another type of neutrino which is right-handed, which where the spin is aligned with the momentum rather than anti-aligned. And so if neutrinos are Dirac, these two different species could exist. And so instead of having one species of neutrino emitted, left-handed one, in the case of a massless neutrino, if we have massive neutrinos, then you would have two species emitted. And so the black hole would radiate more energy compared to the case when neutrinos don't have a mass. So when we started working on this paper, I was interested in this phenomenon that a lot of the literature having to do with the evaporation of primordial black holes consider the neutrinos as massless, but now we know that they are massive, and so I thought, well, strictly speaking, a primordial black hole could radiate more energy than people previously thought. So I found that aspect interesting. And then since you mentioned the possibility to increase the effective number of neutrino species, that's related to what I was talking about. So the black hole would radiate more neutrino states or more neutrino species, so to speak, and then that would increase the number of neutrinos per cubic centimeter that we observe today. So I'm kind of glossing over a lot of details, but basically cosmology gives us a measurement of this N effective, which is called the effective number of neutrino species. And if you have these right-handed neutrinos coming from the primordial black holes, this number could be higher than expected, and so that would be maybe a way to tell that maybe there are primordial black holes in the universe.
Yeah, so the Hawking radiation, essentially radiation coming out of black holes, it is expected, if I understand this correctly, Cecilia, it's expected that over a long period of time, black holes will radiate away, evaporate away all the mass or information that went into it. And so this radiation, is this Hawking radiation, is neutrinos part of that, or is it fundamentally composed of neutrinos?
Hawking radiation is made of every particle that we know of. So a black hole can radiate pretty much everything: photons, neutrinos, electrons, muons, etc., etc. But there is a catch here: the fact that a black hole has a temperature, which is another big achievement of Stephen Hawking and others to show that a black hole is a thermodynamical object. And so basically, the bigger the black hole, the lower the temperature.
Yeah.
So if the temperature is really low, the black hole wouldn't be able to emit very massive particles because the thermal energy wouldn't be sufficient for that. So because mass is energy, mc square, right? So because mass is energy, if a black hole has too low of a temperature, it wouldn't have its quantum energy. Wouldn't be enough to produce the mass of a particular particle. For example, a proton may be too heavy to be produced by a really low temperature black hole.
So the bigger the black hole, the lower the temperature?
Yes.
And so then can we expect the bigger black holes to have more of a neutrino content in the radiation?
Yes, because the bigger black holes wouldn't, as I said, be able to radiate the heavy particles, and so they would only be able to radiate away the low mass particles, and so there could be black holes that only emit photons, gravitons, and neutrinos.
Do we have a sense of sort of the distribution of this primordial black holes? Is it, sort of everywhere? What do we know about, sort of the distribution of PBHs?
You mean spatial distribution, like where they are?
Yeah, no, just so I'm wondering, just like the CMB, if you were to sort of look at the early universe, will we find them everywhere?
Probably at the beginning, they would be more or less uniformly distributed. But in the universe today, they would probably be behaving like the dark matter does. They would be part of galactic halos. In other words, they would cluster gravitationally on large structures like a galaxy or a cluster of galaxies. So if these black holes are still around, they would behave like the dark matter does. So they would be in halos of galaxies.
Wouldn't they have radiated away? Would they not have disappeared because that's really small?
It depends on the mass that they have when they are born. So if their mass is less than a certain value that I'm trying to remember, basically, yes, they would have to. By now they would have completely evaporated. But if their mass is larger, then they would take longer to evaporate, and they could still be around. Roughly speaking, the dividing line between a black hole still being around today or not, I think it's something like 10 to the 15 grams, if I recall correctly.
Into 15 grams. So, so this paper, you say we obtained the diffuse flux of right helical neutrinos from PBHs at the Earth, and so we can actually attribute these neutrinos that we find here to PBHs specifically.
In principle, that's a possibility.
Yeah.
We considered that for certain masses of these black holes and a certain density of these black holes, the flux of neutrinos that they generate over time could be fairly large, and so we could detect these neutrinos if we had a very powerful detector. So now life is never ideal in the sense that a real neutrino detector would have all sorts of issues like background and so on. So at the end of the paper, we conclude that in practice, given the limitations that current neutrino detectors have, it may not really be possible to detect the neutrinos from primordial black holes. But in principle, that's a possibility, and that alone is interesting.
Yeah. Because there was some suggestion that this primordial black holes could be, as you mentioned, could be part of the dark matter that we are still seeking. Is that still a plausible hypothesis?
That has been there has been a debate on this, kind of going back and forth in the scientific community. The latest I heard is that primordial black holes could be part of the dark matter, maybe even a large part, but probably not the entire dark matter. So a 100% primordial black hole dark matter is a bit difficult to justify considering the experimental bounds that we already have, constraints of various types. But there could be scenarios where maybe a fraction of the dark matter is made of primordial black holes.
I want to go into another paper in 2020, Supernova Neutrinos, Directional Sensitivity and Prospects for Progenitor Identification. You say here we explore the potential of current and future liquid scintillated neutrino detectors at kiloton mass to localize a pre-supernova neutrino signal in the sky. In the hours preceding the core collapse of a nearby star, tens to hundreds of inverse beta decay events will be recorded, and their reconstructed topology, the detector can be used to estimate the direction to the star. So this is now neutrinos from supernovas, and so we have an idea here that before the supernova happens, a pre-supernova time period, it is creating neutrinos that we could pick up and potentially get ready to see the supernova.
Yes, that's what excites me. The fact that think about Beetlejuice. Beetlejuice is the most famous nearby star that could go supernova anytime, and we don't know when that's going to happen. And if it wasn't for these neutrinos that our paper is about, we wouldn't know until the star literally collapses and then soon after becomes a supernova. But in this paper, we show that before the star collapses, which is the beginning of the supernova process, we can detect these neutrinos that are produced at that stage. And so in principle, we could know that tomorrow there is Beetlejuice exploding, and that would be quite exciting.
Yeah. So Beetlejuice is a red giant, reasonably close to us, really big star. I can quite remember, Cecilia, there was some suggestion that it could go supernova within something like 150,000 years, which is a blink of an eye in cosmic time. So it is getting ready to go supernova, right?
Yes, I'm not informed about exactly the number of years, give or take, but it's ready. It's ready. It could be any time, and any time for an astronomer means anytime in the next thousands of years. So we shouldn't hold our breath, but it's ready. It could be tomorrow, it could be in 100 years.
Could the supernova, I know that this is not part of the paper, but could the Beetlejuice supernova have an adverse effect on Earth?
Not really, no. A supernova is a very spectacular event. It's a star that collapses, so it implodes first, and that explodes. And then when it explodes, it's very bright. In the case of Beetlejuice, we could see it by naked eye for sure. But in terms of the effect of its radiation and neutrinos and light on us and on our daily activities, it wouldn't affect them in any way. So it's a safe show to just enjoy without any worry.
Right, right. And so you talk about supernova neutrinos. So can we actually detect neutrinos from supernova different from what we talked about in the previous paper, different from PBHs?
I'm not sure. Can you maybe repeat the question?
Yeah, so the neutrinos emanating from a supernova, are they different from the neutrinos we expect to see from a primordial black hole?
Yes, they are different in many ways. These neutrinos have higher energies, so it's much easier to detect them. And in the case of Betelgeuse, we would detect thousands or even more of them, millions probably of them. And they are also different in the way they are born, because in a primordial black hole or in any black hole, the process is Hawking radiation, which is a gravity phenomenon. In a supernova, they are born out of the very hot and dense environment that the star has after it has collapsed. So a star collapsing under its own weight becomes very dense. And so in this very dense and hot environment, nuclear processes take place that produce these neutrinos. So I guess the main difference is that in the case of a supernova, it's mostly a nuclear phenomenon, and in the primordial black hole is really fundamentally a gravitational phenomenon.
Okay. You describe a technique in this paper, and you say it's in principle possible to uniquely identify the progenitor star. So the existing technology and the ideas you discuss in the paper, if we pick up a neutrino, we could identify where it came from or what direction it came from. And then if you go back and look at that in that direction, if you find a supernova, then we could say that is a supernova that created it.
In principle, yes. Yeah. Let me just say that there are situations, and this is not one of them, but there are situations where if you have one neutrino, you can point to the point in the sky where it came from. In this case, it's a little more complicated because what really gives us the information is the statistical distribution of these neutrinos. So we are talking about maybe detecting 100, give or take, neutrinos from, say, Betelgeuse, for example. And what the detector really observes is not the neutrino, is kind of a vector which is related to the products of these neutrinos. So these neutrinos interact with the detector, and then out of this interaction you have a positron and a neutron, and those can be observed. And you can create a vector using these two. And then this vector will have a certain orientation, but each neutrino coming in would give you a differently oriented vector. But statistically, if you look at the distribution of these vectors, you can tell, you can infer with a certain error, of course, the direction of the neutrinos, because these vectors are not uniformly distributed. They are they have a non-uniform distribution of their direction, and so using this information, we can define a region of the sky where the neutrinos could come from. So we cannot narrow down to a point, but we can narrow down to maybe a cone of a few tenths of degrees width. And then we look in that cone and see what stars are in that cone, and maybe Betelgeuse will be one of them.
Yeah, so as you say, so if you see a few neutrinos, the statistical distribution of those will give us some probability that it is in some region of the sky. And then you say in the paper, you can then, that if it is happening pre-supernova, you can alert other observational modalities, multi-messenger observations, invisible in radio and other types of observations to actually pick up more data. So this is almost like an early alert system if it is in place, right?
Yes, I would call it a very early alert, because it's we're talking about maybe hours, or in certain very fortunate cases, we are even talking about maybe a day before the star goes supernova. And so that's enough time to plan for it. So something that fascinated me when I heard about this from an experimentalist is that there is a human factor, which I was not aware of. But the human factor is this. So if you have, for example, 30 minutes to plan for watching a supernova, this may not be enough, because it just takes time to make phone calls and get a hold of people and decide what to do and come to a consensus and et cetera, et cetera. So in addition to technical things like, okay, you have to maybe turn your telescope in a certain direction, which takes time. But I was really fascinated by the human factor of things, that if you have 6 hours, maybe you can kind of gather the relevant people and decide something. But if you have 30 minutes or 5 minutes, maybe not. So,
yeah. I wondered, if such a early alert system is in place, perhaps there could be something programmatic, right? So if it is picking up and you have some, maybe some AI techniques or something like that that identifies the region, and it can then programmatically turn the telescopes to look at them.
Yes,
Maybe.
exactly. So there could be a protocol in place for that. So if a telescope was suitable for observing a nearby supernova, which is not always the case, then now that we showed that it's possible to know beforehand if a star is going to go supernova, then there could be some sort of protocol in place already, so that when the alert comes, we can just activate the protocol and orient the telescope maybe automatically or in some sort of organized way.
Yeah, as you say, if you remove humans from the process, it becomes a lot better.
There is actually already a work in this direction. It's called the SNEWS 2.0 network, which has to do with exactly this, using neutrinos as an alert for the astronomy community. And that has to do with exactly creating alerts and also creating protocols for how to react to an alert.
Right, right. I want to go into another paper that just came out, a concordance scenario for the observation of a neutrino from the Tidal Disruption Event 80-2019 DSG. You say we introduce a phenomenological concordance scenario with a relativistic jet for the Tidal Disruption Event DSG 80-29 DSG, which has been proposed as a source of the astrophysical neutrino event IceCube. So the tidal disruption event, this is a star getting closer to a black hole, getting sucked in, right? Is that the event?
Pretty much, yes. This is something that we hear about maybe in popular science talks. What happens if you get too close to a black hole? And it's kind of scary. So the answer is you would be ripped apart because your feet will be pulled in with a stronger force than your head. And this is what happens to stars. If a star gets too close, then it gets ripped apart, which is what this tidal disruption means. And so instead of a star rotating around a black hole, we just have a stellar debris that are eventually accreted by the black hole.
Right, right. Yeah, and so this is something that we have been able to observe. So we have this, we know this happened, right? This particular event, 80-2019 DSG, and we could actually see neutrinos from that particular event.
So tidal disruption events are a fairly well-established phenomenon in astronomy. We have many of them observed. They are fairly commonplace events. But what's special about this particular one, 80-2019 DSG, is that it could, let's say, it could have produced a neutrino that was detected at IceCube. So 80-2019 DSG is the first tidal disruption event for which there is a coincident neutrino detected at IceCube. And this coincidence is unlikely to be accidental. So a probability estimate tells us that this coincidence is probably causal, not accidental. So 80-2019 DSG could be the parent of this neutrino, and that's a first. That's very interesting.
Yeah, so IceCube is a big ice cube in the South
It
Pole.
literally
right?
is. I'm not sure it's exactly a cube, but it's a big block of ice which has been instrumented with various small detectors. So it's an array of smaller detectors. But yeah, it's basically a big block of ice which has been transformed into a detector.
And so the idea there is that this high energy neutrinos from whatever system, whatever event that happened out there, this high energy neutrinos passing through that ice cube will leave some telltale signs of that happening. And if we pick that up, then we can trace that back, just like you were talking about in the previous paper. We can trace that back to a region where that might have happened.
Yes. So this is one of those cases where you can tell from a single neutrino, of course with an error, where you can tell the point in the sky where the neutrino came from. It's doable with one single neutrino because these high energy neutrinos, when they enter the ice, they produce a shower. So they kind of illuminate the ice. but they do it in a way which is very much beamed. So, and then the direction of the beam tells us the direction of arrival of the neutrinos with a pretty good accuracy.
So how often could we pick up something like that? Do we have an estimate of how often that would happen? Meaning, IceCube detects something like this.
Every year, IceCube detects of the order of 10 high-energy neutrinos from outside our galaxy. So that's the number for the entire crop, say, of neutrinos that IceCube has. When we talk about tidal disruption events in the specific, these are fairly rare phenomena. And so the estimate is that maybe a few tenths of percent of the entire neutrino flux that IceCube is observing could be from tidal disruption events, not much more than that. So we are talking about less than half of the total flux being due to tidal disruption events.
Okay. And so the tidal disruption event, as you mentioned, a star getting ripped apart and pulled back into a black hole. But these 10%, do they have to be these blazars, as they call it? So, things that have a jet that is sort of aligned towards us. Is that a necessary condition for these types of high energy neutrinos?
It's a plausible scenario. Let me just say that there is an important difference between blazars and tidal disruption events in the fact that a blazar is something that has a jet which is always on. So the jet is kind of a permanent feature of this particular galaxy. But a tidal disruption event is a transient event. So the star comes, creates the accretion, this accretion of the star on the black hole produces a flare, and this flare can last maybe for a year or two, but then it will just fade away. So there could be a jet, and in fact, in our paper, we present a model where there is a jet. So the hypothesis is that there is a jet. But if there is a jet in a tidal disruption event, that's a transient one. It's a jet that's born when the black hole starts to accrete the stellar debris, and then it's on for months or years, and then shuts off. And it has to point in our direction, as you mentioned, because otherwise we wouldn't see the neutrinos.
Yeah, so these high energy neutrinos, Cecilia, how many orders of magnitude are we talking about compared to the ones that we pick up, let's say, from the sun?
I'm not sure about the question. Can you maybe rephrase?
Yeah, so when you say this high energy neutrinos that is coming from, let's say, a tidal disruption event or something like that, how many orders of magnitude more energy are those compared to the ones that might be created in the sun, for example?
Okay, many orders of magnitude. So there is a big difference. So the sun produces neutrinos over a wide range of energies. The higher energy neutrinos from the sun reach energies of the order of 10 MeV, 10 mega electron volts. And for the IceCube neutrinos, we are talking about 100, of the order of 100 TeV, or even 1,000 TeVs, which would be a PeV. So let's say maybe 8 orders of magnitude, if I've done the math right.
8 orders. Okay. And so this EV measure, it is actually measuring the mass
of the neutrino.
of the neutrino?
No, these neutrinos are have such high energy that
Yeah.
basically it's impossible to know their mass because as I said, mass is energy. So the total energy of a neutrino detected at IceCube is so high that the percentage due to its mass is so tiny that it's practically negligible. So
Yeah, I was wondering if we know the energy, couldn't we sort of back compute, like you say, what the mass is, or it doesn't follow?
the reasoning is a bit different. The way to think about this is perhaps the let me see the formula for the energy of a particle, which
Yeah.
is the rest energy plus the kinetic energy, and so the kinetic energy is so high that it totally overwhelms the rest energy. So it's
Okay.
and of course every time you measure the energy of a neutrino, there is an error associated with the measurement. So we can't really tell what the mass of the neutrino is.
Yeah. But more broadly, this appears to be sort of an early warning system for many things, right? We talked about the supernova. If the tidal disruption events are producing high energy neutrinos, so this could be sort of integrated with the multi-messenger observations protocols, as you mentioned. That gives us a higher success rate, I would think, to observe phenomena we want to observe.
That's right. That's the power of multi-messenger astronomy. The integration of different signals coming from photons, neutrinos, gravitational waves, cosmic rays, and the interplay is very powerful. In many cases, and maybe the supernova case is the most striking one, the neutrinos come first, but that's not always the case. So in the case of tidal disruption events, the neutrino that was observed came about 5 months later than the initial astronomical observation of the tidal disruption event. So it can go both ways. Neutrinos can be the early alert, or the early alert could be, for example, a radio observation or an X-ray observation, and then the neutrino detector could focus a search in that direction and see what they find, which has actually been done. IceCube sometimes does these archival searches on the basis of alerts from for example X-ray or gamma ray surveys.
Yeah. Yeah, I mean, it is an exciting area. There is a lot to be learned. It seems like we still don't know all the production mechanisms for neutrinos. But if we have a robust way to pick them up here on Earth, then we can trace them back and and start asking questions. What might be there?
Definitely.
So if you so if you look forward, Cecilia, in the next 5-10 years, um, what are the areas that you believe we will make significant progress in this in the area of neutrinos?
There are two different areas that are very promising. One is, broadly speaking, man-made neutrinos. So there is a big push, especially here in the United States, to build create very powerful beams of neutrinos. And then these beams are man-made, so we know them very well. We know their energy, we know their composition, and we can use them to learn about the properties of neutrinos. And then there are other man-made neutrino experiments where scientists look for the neutrino mass. So that's also very promising. And it's something I'm really excited about, that maybe a few years from now we will know what the neutrino mass is from these very high precision laboratory experiments. Then there is the whole topic of neutrinos as part of the multi-messenger astronomy. And in that area, I think what's to look forward to, among other things, is the interplay with gravitational waves. Gravitational waves is still somehow a science of its own to a large extent, but there are so many possible connections with neutrinos. Tidal disruption events should produce gravitational waves. Supernovae should produce gravitational waves. So there is a lot of potential there, which is still unexplored, and that's where I see myself working on in the next few years.
Yeah, just very quickly, do gravitational waves travel very close to the speed of light? And so do neutrinos, right?
Yes.
And so if they both are produced in an event, then they're expected to arrive on Earth close to simultaneously?
It depends on the timing of the production. If the answer is yes, if the gravitational waves and the neutrinos are born at the same time, which may not be exactly true, because the physics that governs gravitational waves is different from the one that governs neutrinos. But the difference in timing would be the difference accumulated at birth. But if the two were generated at the same time, they should arrive at the same time.
Yeah, I was just thinking, if there's a systematic difference in the production time, then one will always give an early warning for the other. But that doesn't seem to be the case, right?
There could be cases where there is a significant lag in the production of a gravitational wave with respect to the production of the neutrinos. And one example is, we haven't touched on this before, but let me just mention mergers. So if we have a merger, for example, we have maybe a merger of two neutron stars, or one black hole and a neutron star. Before the merger happens, so when the two objects are kind of still approaching each other, we should start observing gravitational waves, and this is what has been seen. So the LIGO experiment observes this phenomenon. But if we have a merger, after the merger has occurred and the two objects have become one, then there could be the formation of an accretion disk, and this accretion disk could produce neutrinos, which we can detect. So in that case, the neutrinos will come after the initial observation of gravitational waves, and so the gravitational waves will be the alert for the neutrino detectors.
Right. Excellent. Yeah, this has been great, Cecilia. Thanks so much for spending time with me.
Thank you for inviting me. It was my pleasure. Okay,
absolutely.
Thank you.
Bye. Bye.
This is a Scientific Sense podcast providing unscripted conversations with leading academics and researchers on a variety of topics. If you'd like to sponsor this podcast, please reach out to info@scientificsense.com.